All right, let's go on a little journey. We're going to start with something you probably think you know pretty well and see how it blossoms into one of the most powerful ideas in all of mathematics. We are talking about vectors. But believe me, there's so much more than just little arrows.
So let me ask you this. What do an arrow, a polynomial, and a matrix have in common? I know, it sounds like the beginning of a really nerdy joke, right? But I promise you, by the end of this, you'll see how they're all part of the same exclusive and very powerful club. This question, well, it's the key to everything.
You know, when most of us hear the word vector, our minds probably jump right back to physics class. We picture an arrow floating in space. It's got a length, its magnitude, and it's pointing somewhere, its direction. It's perfect for describing stuff like the velocity of a car or the force of gravity. And that's our starting point. That's the familiar ground.
So let's start on our home turf, this comfortable world of 2D and 3D space, or what mathematicians like to call R to the N. Because, before we can break the rules, we've got to understand them first. So how do these arrows actually behave?
Well, it turns out it's all based on two really simple moves. We can add two vectors together. You just add up their matching parts, and you get a brand new vector. And we can multiply a vector by a plain old number, a scalar, which lets us stretch it or shrink it or even flip it around completely. These two basic operations, they're the foundation for literally everything else.
Okay, so if those are the moves we can make, what's the rule book? What are the fundamental properties that make this whole game work? This is where we start to uncover the blueprint for what really makes a vector a vector.
Now, when you look at these 8 rules, you might be thinking, yeah, okay, so what? I mean, of course, u plus v is the same as v plus u. Duh. And of course, adding 0 doesn't do anything. We've kind of taken these things for granted our whole lives. But writing them down like this, all in one place, it is so important. These aren't just random observations. They are the fundamental laws that make vectors work the way they do.
And this right here is where we take the big leap. This is the moment everything changes. What if we stop thinking about a vector as a thing, as an arrow, and instead we start thinking about it as any object, anything at all that just happens to play by this exact same set of rules? This simple but totally profound shift in thinking lets us do something amazing, what I like to call the great generalization. We're going to take that rulebook, that blueprint we just uncovered, and use it to build something way bigger, way more abstract, and way more powerful, the idea of a vector space.
So here it is, the official definition. A vector space is just a collection of things, we'll call them vectors, just to be nice, that has a way to be added and a way to be scaled, and follows 10 specific rules, or axioms. That's it. Notice it says nothing about arrows or magnitude or direction. And would you look at that? The official rulebook is basically the 8 properties we already found. The only new ones are those 2 at the end, the closure axioms. And all they say is if you add 2 things from your set, the result is also in the set. And if you scale something from the set, it stays in the set. It's kind of like a club with a velvet rope. What happens in the vector space stays in the vector space.
So, if any collection of objects that follows these 10 rules gets to be a vector space, who else gets to join the club? This is where it gets really fun. Our whole universe is about to expand. Let's meet the new members.
Get this. You can add 2 matrices together, right? And you can multiply a matrix by a number. Well, it turns out those operations follow all 10 axioms, which means a matrix can be a vector. Wild.
And it doesn't stop there. Think about polynomials. You can add them, you can multiply them by a constant, and, yep, you guessed it, they obey all 10 rules. So, a polynomial can be a vector too.
But this is the one that really gets me. The set of all real valued functions, that's a vector space. This means an entire function, something like sine of x, can be treated as a single vector. We've come all the way from a simple arrow to this. It's just mind-blowing. Okay, I can hear you thinking it. That's a cool party trick, but so what? Why are we twisting our brains into knots just to call a polynomial a vector? Well, this is where the real magic happens. This is why it all matters.
It's because once we prove that a collection of things is a vector space, we get to use our entire toolkit of geometric ideas, concepts like length, distance, angle, and dimension, on problems that don't seem geometric at all. We can bring our spatial intuition to worlds that have nothing to do with space.
Think about it like this. We all get what an XY coordinate grid is for arrows on a piece of paper, right? It gives every point a unique address. Well, the abstract big brother version of that is something called a basis. A basis is a coordinate system for a vector space, and it lets us give a unique address to every single vector. Doesn't matter if it's an arrow, a matrix, or an entire function.
I mean, the textbook says it perfectly. A basis is the vector space generalization of a coordinate system. Let that just sink in for a second. It means we can navigate these incredibly complex, high-dimensional worlds of functions with the same kind of map we use to find a point on a 2D plane.
And that leaves us with one last, kind of wild thought to chew on. A sound wave can be described as a function. We just said functions can be vectors. So, if we can create a coordinate system, a basis, for the vector space of sounds, what would that look like? What could we do with it? Maybe, just maybe, we could describe any sound in the entire universe with just a short list of coordinates. Now think about that for a minute.